why is this inflating? It's because I'm putting air in here. I'm taking molecules of oxygen and nitrogen, maybe even some carbon dioxide, and I'm putting them inside this balloon. That means that inside the balloon, they now occupy a volume. They have a shape. And that gas, as a volume, is now subject to something known as pressure. Now, when I blow up this balloon, there is actually the pressure of the gas on the inside, and there is the pressure of the air on the outside. And when these are in balance, the balloon stays this size. If I increase the pressure by adding more air, the balloon indeed gets bigger. But what would happen if I then tried to compress the air in this balloon? Well, it would kind of spill out of the sides. But what if I stopped it from doing that? Is this gas compressible? In fact, you find that it is. Now, just here, I have a piece of apparatus known as Boyle's law. And Boyle's law is simply a tube of gas and then there's some oil underneath. And don't worry about what the oil is doing, it's just trapping the gas in. And what I'm going to do is I'm just going to put it under more pressure. And the way I'm going to do this is I'm basically going to fill up this space with some air, and that's going to press the oil, and what's going to happen is that oil is then going to compress the gas. So if I, at the moment you can see it is on 0, should be on 0, well it's not on 0, it's at it's air pressure, which on the outside you can see is about 100 kilonewtons per meter square, or 100,000 pascals. If I put some air in, the pressure goes up. I can send it to there, a bit more. That is about twice air pressure. And did you notice that the gas in this section here has compressed? I can put this under more and more pressure. In fact, what I could do is I could record the data. I could actually record what the pressure is and what the volume of the gas is and see what that looks like. What I'm going to do is I'm going to create a column with pressure, volume, and then I'm going to leave a third column here for something else in a minute. There we go. Best table ever. Pressure is measured in pascals. Volume is measured in, I presume, centimetres cubed, but it doesn't really matter. I'm just measuring these two things. Normally volume would be measured in metres cubed, but this apparatus has got something else on it. To start with, the starting pressure is 100 kilopascals. So let's put the kilo at the top just to make it simple. 100, and the volume of the gas is exactly 40 centimetres cubed. So let's go to, what should we do? Let's go to 200, and we find that it is about 20. If we go to 300, it was about 12 and a half. Go to 400, and hopefully it doesn't explode. Oh my gosh, 400. Oh, what was it? It was about 10. I can actually hear the air leaking out of this apparatus. It's probably fairer to it to let it decompress. There he goes down. And so that is my data. Not the best, but what I just want to show you is this really weird thing. 100 times 40 is equal to 4,000. 200 times 20 is equal to 4,000. 300 times 12.5 is nearly 4,000, 43750. 400 times 10 is, oh look, 4,000. So that was an anomaly. I must have read it wrong. What we know is pressure times volume equals a constant. Let's explore what that means. I have here a table and I'm going to put the data in. So the first measurement was 100 kilopascals and the volume measurement was 40. The second one was 200 and the volume measurement was 20. Now on the next measurement, on 300, we identified an outlier. It wasn't quite equal to the constant we expected. So I retook the data. I went back, had another look, and found exactly what it should have been. And the actual answer is 13.3. And finally, 400, and it was equal to 10. Now, a good question here is, why does it equal a constant? And what does that constant mean? Why does it equal 4,000? Does it always equal 4,000? Or is 4,000? Well, it equals 4,000 in that particular setup. The 4,000 is connected just to how much gas I've trapped in that tube. If I had a different tube with a different amount of gas, then the constant's going to come out completely different. Also, we did this at room temperature. If I did it in the freezer, then that constant would have a different value. The temperature and the amount of gas determine the actual number that that constant is. So if we keep it at room temperature, and we always use that same amount of gas, that constant is going to be the same for each one of these volume and pressure measurements. So that's what it looks like on a graph. I've got pressure on my y-axis and volume on my x, but I could swap them around, it doesn't really matter here. So pressure of 100 is 40. Pressure of 200 is 20. Pressure of 300 is 13. And pressure of 400 is 10. So there we have a lovely relationship. When one is large, the other is small. Look, when pressure is large, the volume is small. When the volume is large, it must be because the pressure is small. Think about what this means. If you put something under pressure, you squash it down smaller. If you allow it to, if you take that pressure off again, and the pressure lowers, then obviously it's going to spring back. And the gas is springy. Right, a balloon, and a really little balloon. Now, what's different about these two? It's just the amount of gas that I've put in. They're both the same temperature. It means that the pressure volume product is not going to be equal to the same constant. That there is just a higher constant for this because there's more material in it, and the constant is smaller for this. But what has happened to both of these is they have occupied the correct volume for the amount of pressure that's inside. But what determines the pressure that's inside? Well, the pressure in here is pretty much the same as air pressure, maybe ever so slightly more because the elastic is squeezing it. But basically it's reached a nice equilibrium, a nice balance where the air pressure on the outside is equal to the air pressure on the inside, and that's why it's staying the same size. Obviously being much smaller, there's a lot less gas in here, and so the point where these two things balance is when the balloon is this size. This one, it balances when it's this size, and so you can see that's what causes the difference. Now I can make it bigger by adding more gas inside. If I increase the amount of gas inside, the pressure would go up, it would try to expand to a larger volume, and until eventually it reached the volume that enabled the pressure on the inside to match the pressure on the outside. But what if we lower the pressure on the outside? Well, what I have here is a vacuum generator. Now underneath this really heavy glass jar, which is really stuck, I can't seem to get it to come off. Come off. Yeah. Yeah, hang on. Okay, oh, it's off. I'm going to place the little balloon inside, and we'll smear this back on. We need a really firm. There we go, no gaps. Now I'm going to hit the power, and we're going to suck the air out on the outside. Look what happens. So I start sucking the air out from the outside. Now what happens is the gas on the inside is trying to stay the same pressure as the gas on the outside. Wait, that's it. And what you can see happening is for the pressure on the inside to equal the pressure on the outside, it has to occupy a larger volume. So I'm inflating this balloon, not by adding any air on the inside, but just reducing the air pressure on the outside. With how big is it going to get? Now, if you ever wondered what happened when you launch or let go of a helium balloon and it drifts off into the atmosphere, well, it goes higher and higher and higher where the atmospheric pressure is less and less and less. And what starts to happen is the balloon actually starts to expand and get larger. And it does so because the pressure on the outside is much less. And of course what happens is it has to occupy a much bigger volume for the pressure on the inside to balance the pressure on the outside, until eventually they all pop. So the idea that all of those helium balloons are lost in space and gathering on the moon is totally false. I think this is about as much air as we can suck out of this one. So what we'll do is we will allow some air back in, turn this off, allow some air back in, watch what happens to the balloon. Air is being sucked in and it is crushing the balloon back to its original size. This is a piston. And what a piston is a small chamber that has a little moving sliding rod that can put the gas that is here under significant pressure. Now, pistons are used in many different places. This is a model of a diesel engine. You see these in all kinds of diesel cars and motor vehicles, lorries and the like. Now, how it works is it takes the vapour from the diesel, and which in itself is not a flammable substance. And what it does is it basically squashes it down until it's under high pressure, at which point it does become a flammable substance. And the way it does that is with this piston. You can see that what happens is this piston gets pushed up and the gas in this section here becomes really quite high pressure because the volume has been reduced. And whether or not it's a diesel engine or a petrol engine, the way in which it works is we squeeze down the volume and it increases the pressure, the concentration of the fuel in this section here. But a very good question is, what happens if we press a gas? What happens in terms of the energy? Imagine that all of the particles inside are bouncing off the walls, and their speed is linked to their kinetic energy. The more they move, the more kinetic energy they have. But that itself is what we measure on the outside as temperature. That the more kinetic energy they have, the warmer it is, the higher the temperature. Now imagine this, if we decide to change the volume of this container, if we go from having a static surface that this gas can bounce against to us moving it down, it means that now the ball not only has all of the velocity that it had but now in another direction, but it has a little additional bit of velocity. There's a little bit of extra movement. It is not just its velocity being returned, it now has its velocity plus a little bit more velocity from the bat. It makes sense that if I can hit this at 50 meters a second, if I was on a train and I hit it, I would be able to hit it with a speed of 50 meters a second plus the speed of the train. That if I move the piston down, it's going to give all of those things that are bouncing off it just that little bit of extra motion. But here's an interesting thing, right? Surely that motion is of no consequence, because these are bashing around at hundreds of meters a second. This piston is going down slowly. No, it doesn't make very much difference to one of these particles, but you've got to remember that in here there are billions. And if you make a very small difference to billions of particles, then they're all going to end up with a tiny bit more kinetic energy. And so what's going to happen as you do work by applying this force through a certain distance, it's going to mean that the kinetic energy of all your particles are going to go up just slightly, meaning the temperature is going to rise. The result of doing the work on a gas is that the temperature will rise. Right, so I have an inner tube from my bicycle, and I'm going to inflate it. I'm going to use a piston here to compress the air to make it move into that tube so that it's in there. This piston is compressing the air. Here we go. Now, compressing the air, like I've just done, will have done work against the gas, and you can see through this thermal imaging camera, if I can get it to point at the right thing, that it is now significantly warmer. That doing work against a gas has increased the temperature of the gas and of the piston. This piston is in fact a fire piston. How a fire piston works is that you let some air in there, and then you put this on and you compress it so fast that the temperature rises in this small section here because of the work you're doing on the gas. It rises so much that the air itself explodes and sets on fire. So if compressing a gas makes it get hot, then imagine what happens when you decompress it. If this plunger is moving upwards, every time a ball strikes it, it is now not going to return with all of the velocity that it originally had, because it's going to have its original speed minus the speed of this, rather than in the compression it was the speed of this plus the speed of this. Now, because this is moving the other way, it's the speed of this minus the speed of this. It means that every one of those return bounces is going to be leaving the particles with just a little bit less kinetic energy than they had before. Decompressing a gas makes it cool down. Now, don't mind me, I'm just doing a little bit of dusting. You know how I've got to keep things spick and span. I have here a canister of basically air, compressed air, in a can. Now if it's compressed in the can, then work was done against it to compress it into the can. As I allow it to decompress, then that energy is then available to come out. It's going to basically come out colder than the gas that is in here. And what I'm going to do is I can basically, I can spray something and I can look at it with the thermal imaging camera. So if I spray the wall here, and you can see I'm actually creating, I can write my name. That's the worst hello I've ever seen. But basically what comes out of a canister like this is colder than the air around it, and that's basically because of the fact that it's decompressed. Now that means that an aerosol can will feel cold on your skin. It also means that other things that are put under pressure, like a fire extinguisher, will come out really, really cold indeed. When you operate a fire extinguisher, it's really important not to hang on to this metal bar, because you will get so cold you will stick to it. You're supposed to hold the plastic thing, which is an insulator, and it doesn't suck the heat from your hand. But this idea that a decompressing gas will draw the heat out of things and it will be itself colder than the environment is the basis for the operation of a refrigerator. This is a refrigerator taken apart. Now, with both fridges and freezers, they work on this principle. The small motor that is around the back is compressing a gas, and that happens outside of the white box. It means that work is done against the gas, and it results in the freezing fluid, I should say, basically getting quite hot, but that heat is radiated out of the back of the refrigerator. The pipes containing this fluid then go within the refrigerator, and deep inside here what happens is it is allowed to then decompress, and when it decompresses it reduces the temperature to below that of the environment around it. And that's why it's colder on the inside of a fridge freezer than it is on the outside.